Right. Okay, so here, this is just a review of what we did last time. So just remember that for any non-negative integer n, we can define n factorial. We can do that. Okay, if you remember, if n is positive, meaning n is greater than or equal to 1, then n factorial, you basically multiply all the integers, all the positive integers less than or equal to n together. This is if n is positive. You multiply all the positive integers together less than or equal to n. Okay, that's how n factorial is defined if n is greater than or equal to 1. For 0 factorial, remember, by definition, that's just 1. That's just defined that way. I want to say for convenience, but if there's another reason, I don't know why it's defined that way, but I think it just works out well when it's defined that way. And we also saw permutations. If you remember, if you can't see the notes or you can't hear me, let me know. If you remember also with permutations, right? If you have n items and you're arranging r of them where the order matters and without replacement, meaning there's no repetition. Okay, that's what without replacement means, basically means no repetition. And order matters, right? So the order does make a difference. You have permutations, and the total number of possible arrangements is given by this. Again, this notation is a little bit different than what the book does. Personally, I like this notation better. I mean, you could calculate it directly using these factorials, or you can just use Desmos. Some calculators do have, I don't know if it's this notation, but some of them do have this programmed in their calculators. I don't think the calculator for the iPhone does though, but I don't know about the Android, but I do know for Desmos, you can do permutations with it. Okay. Also, if we're arranging r out of n items, okay, if we're doing that, but order matters and we allow repetition, so with replacement and we allow repetition, okay, then the total number of possibilities is n to the r. I don't know if this is called anything special. Like here, these were permutations. I don't think these are called anything special, but again, the total number of possibilities here, this is with replacement, so repetitions allowed, and the order does matter. Then the total number of possibilities is n to the r. N to the r, okay? Again, it's really just based on the counting principle. Speaking of which, I wrote the counting principle in a different way. I actually got it from this website, Math is Fun. It's a nice website. If you want to check it out, that's up to you. But I put the website here. They state the counting principle in a way that I think at least is easier to understand. Basically, if there are m ways to do something, to do one thing that is, and there are n ways to do another, then to do both, there are m times n ways. In other words, you just multiply. That's really what it's saying. That's all you do. That's what they're saying. You just multiply. There we go. Okay. So that's what the counting principle says. I mean, we did do it last time, but I wrote down what was in the book. I mean, what the book said, I thought was easy to understand. I just think this is a little bit easier. So, all right. So let's do an example. Excuse me. Let's do an example. So here, what we're going to look at is we want to make a 6-character password. So a password that has 6 characters in it. we can use any letter from the alphabet, you know, A through Z, and we can use any digit 0 through 9. Okay, 0 through 9. So we can use any one of those. Let me just get Desmos up here. There we go. Okay. Okay. Just wanted to get Desmos up. Okay. All right. So again here, so the question now is, how many possible passwords are there if we allow repetition? So remember, with a password, order does matter. Sometimes we allow repetition, sometimes we don't, okay? But here, we do allow repetition. Okay, so for each character, there's 26 letters plus 10 digits, so there's 36 possibilities, right? 36 possibilities. So because of that, how many possible passwords are there? Well, again, we're just using here, since we allow repetition, you know, with replacement, and since the order does matter, n to the r, so in this case, it would be 36 raised to the 6 possible passwords. I don't remember how big a number that is. I want to say it's at least 1 billion. Well, it's probably 2 billion at least. But anyway, there's a lot of passwords. Okay? So that's what we get here. Now, let's find the probability of choosing. Now, we're going to find the probability of choosing a password, but with no repetition. So order does matter, but now we're not allowing repetition. So that tells us, right, we're looking now at permutations. Because we want the probability of, basically we want to know what's the probability of choosing a permutation, a password that is a permutation. Okay? Now, well, how many permutations are there? Well, we know that there are 36. We're making an arrangement of 6, that's 6 units long, you know, a 6-character password. And each character, there are 36 possibilities. So again, we have P of n r with 30, n is 36, r here is 6, right? N is 36, r is 6, right? Okay, well, how many permutations are there? P of 36 comma 6. I mean, if you did use the factorial stuff, this is what you would get. In Desmos, in Desmos, if you typed it out, right, you would end up getting this amount. You know, I would make sure, if you're going to use Desmos, make sure, you know, you get the right answer like this. Okay. All right. Okay, so that's how many permutations there are. What's the probability then? You divide, right? Divide like this. When you divide, what do you get? You get this here. Now, I didn't round it, I know, but, you know, that's what you get. Sorry. Oh, man, changing weather. All right, so that's what we get here. Okay, so do you have any questions about this example? I mean, if not, that's okay, but if you have questions, don't be afraid to ask. Okay. Well, all right. So this is actually where I left off last time. I figured it wouldn't be a bad idea to review from before. So, you know, that's what we did in the previous slides. So here, right, we want the probability. So here, basically, we have the probability of an event happening at least once. That can be tricky to find, you know, that could require many cases, you know, what if this happens, what if that happens? What's nice, though, is we have a way that can help us, namely this formula. With this formula, right, we have the probability of an event happening at least once. That's equal to 1 minus the probability an event never happens. And why is it this? Well, because the complement of an event happening at least once, how could that not happen? Is the event never happens. The complement means the event doesn't happen. Whatever it is you're considering, it doesn't happen. So the complement of the event happening at least once, meaning this does not happen, the event does not happen at least once. Well, if it doesn't happen at least once, it can't happen at all. It never happens, in other words. And so I'm just using a formula we saw earlier, the probability of an event plus the probability of an event equals 1 minus the probability of its complement. And that's what I'm using here. And sometimes it could be the other way around, where this could be very hard to calculate, but this is not. So, the formula is helpful. In fact, let's consider an example, just quickly applying it. So let's say we toss a two-sided fair coin 3 times.